Well, welcome everybody. This is the FLOW seminar, where FLOW stands for Federated Learning One World. That was a seminar that created to provide a global online forum for the dissemination of latest scientific research results in all aspects of federated learning. And today is my great pleasure to introduce you our speaker, Constantin Philippenko, who is currently a postdoctoral researcher at DNs and INRIA Paris, working with Kevin Scammon and Laurent Massolier. He obtained his PhD in applied mathematics and computer science from École Polytechnique under the joint supervision of Eric Moulin and Aymeric Dulevet, both professors at the CMAP laboratory at École Polytechnique. And today he's going to tell us more about his recent research on compression in federated learning. So thank you, Constantin, for agreeing to give a talk. Floor is yours.
Thank you very much, Samuel. It's a real pleasure and an honor for me to present my work at the FLOW seminar. So today I will present a joint work with Aymeric Dulevet that has been published at GMother. So I will speak about distributed least square regression with compression, and I will apply it to federated learning. So do not hesitate during this presentation to interrupt me and to ask a question. I will be very happy to answer them as they come. So in this presentation, I will first present the framework for compression. Then I will give very general results on linear stochastic approximation. Then I will apply to compressed least square regression on a single client, and then I will apply all these results to the federated learning setting. And then I will conclude this presentation. So first of all, our goal is to learn from a set of n clients, each holding their own local data distribution di, which might be different from one to the other. And we have our model W, and we want to minimize the global cost function, which is the average of all local losses. To do so, we use a distributed stochastic gradient descent, which consists in computing a gradient on each client and sharing this gradient to the central server. The central server aggregates together all these gradients and share back to each client in order to update the model and to compute WK. In the setting of federated learning, there is a lot of challenges, but in this presentation, I will focus on two challenges. The first one is to handle heterogeneous clients. In this presentation, I do not assume that all clients share the same data distribution. But the main challenge that I will focus on is the communication cost. I want to reduce the communication costs, and to do so, I introduce a compressor C that compresses the information shared from the client to the central server. Of course, I could also compress back the information from the central server to the clients, but here the main of this work is to analyze the impacts of compression, and this is why I only compress one way. So now the update equation is slightly changed, and instead of aggregating the gradients, we aggregate the compression of each local gradients. To give a few insights on compression, in this work, we consider two big family of compressors. The first one is sparsification based. So for instance, round H, which keeps H coordinates. There is also P sparsifications, which keeps each coordinate with a probability P. Another one is P partial participation, which is a very simple one. It's one of the natural setting of federated learning, where a client is not involved at every round, and we assume with this compression that a gradient is sent to the central server with a probability P. Either everything is sent, either nothing. The last compressor that I want to present in this family is sketching, where we sample at each round a random matrix in order to project our gradients into a lower dimensional space. The other big family of compressors are quantization, which are based on a codebook. For instance, there is S quantization, which code the information on S level. if we only have one, if we consider one computation, it's either send 0, either the norm with a given probability. Okay, so the big question that I'm asking in this work is, what is the impact of a compressor C on convergence?
Yeah. Can I ask a quick question?
Yes,
Oh,
sure.
okay. I think I think you just answered. I just wanted to ask like whether the compression that you analyze has to be unbiased or you allow the bias.
Yes, so this is exactly what I was going to mention. So thank you very much for this transition. So yes, here I consider the following assumption, which is very classical, and lots of papers are doing it. So here I'm assuming that the compression is unbiased, and that its variance is relatively bounded by constant omega that characterize the compression. So the bigger is omega, the more drastic is the compression. So when considering unbiased compressors, this assumption on the variance is classical and is made everyone. So this is the classical assumption that every paper on unbiased compression is doing. Here my goal is to go beyond this worst case assumption and to provide a tighter analysis. To do so, I focus on the linear or the least square regression framework, which is popular for fine-grained analysis, as its simplicity allows to analyze more complex problem. So here, the final goal of this presentation is to highlight difference in convergence between several unbiased compression schemas that have the same variance. So these behaviors was not captured before, was not observed, was not captured by previous theories, because there was all previous works are only considering this worst case assumption. And I show that we might have two compressors that have the same assumption, but that in practice have very different behaviors. And I will explain why. So in the first part of this presentation, I will consider the simplified setting with one client. I will then extend it to federated learning. This is only to have the key insights. And I assume that each client have access to key ID observations that consist of a pair of features and outputs. And I assume that there exists a well-defined model W star, such as that the output is equal to the scalar product between the features and the well-defined model plus a term of noise, of random noise. Okay, just to motivate this work, let me compare 5 compressors in 4 different behaviors. And let me show that they have 4 totally different behaviors. So here in the first one, so let me first explain what I represent. So on the x-axis, I represent the log of the number of iterations. And on the a-axis, I represent the logarithm of the excess loss evaluated at the Polyak-Rupert iterate. So here I have 5 compressors, and in blue, the benchmark without compression. Here, what I observe that most compressors have a linear rate of convergence in a log-log scale, so which is characteristic of a one-key rate of convergence. Almost everyone, except the red one, which is sketching, which at some point starts to saturate. And in orange, which is one quantization, at some point it starts to be slightly worse than the 3 others, pacification, round H, and partial participation. But it's still comparable. So this is the first scenario. In the second one, I observe that now only the brown one, which is partial participation, is comparable to the benchmark without compression. And for some reason, all the others behave equivalently badly and saturate at some point. In the third one, all compressors are equivalent and behave well. And in the last one, now we observe that quantization are partial and partial participation are very good. They behave almost like the benchmark without compression, while sketching, sparsification, and round H behave quite badly. So the big question is, can we explain these 4 different behaviors? And the answer is yes, otherwise I would not be here to present this work. Okay, so before explaining the behaviors of these different compressors, I would like to take a step back and to analyze a more general problem. I would like to analyze linear stochastic approximation problems. So I assume that my model WK is updated based on three quantities: my past iterate, a true gradient evaluated at the past model, and a term of noise. This term of noise Xi is a sequence of ID zero-centered random fields that characterize the stochastical oracle. Here we assume that F is quadratic, and therefore we note HF its Hessian and mu its smallest eigenvalues. So noting eta k, the difference between our iterates and the optional iterates, W star, we can rewrite the update equation as a contractive term and a term of noise. So this is what the problem that we will analyze in the first part of this presentation. Just to give you an example why this is relevant to our use case, for the case with a single worker without compression, well, the noise is simply equal to the difference between the true gradients and the stochastic gradients. Now, with compression, we have our model that is updated based on the previous iterates and the compression of the gradients. Well, our random fields is simply the difference between the true gradients and the compression of the stochastic gradients. So most analysis of this problem assume either that the random field is linear, either that it's Lipschitz in square expectation. This problem is very classical and there is a lot of analysis. So it's not something new, but the bottleneck and specificity of compression is that the resulting random field does not satisfy such an assumption. So this is why we cannot take all the existing results on linear stochastic approximation and apply it to compression. We need to find a new assumption that is verified by the random field in order to analyze this problem and to provide non-asymptotical rate of convergence. So I don't know if there is any question at this point. Is the setting clear?
I think it's very clear, but if anybody has a question, please feel free just to unmute yourself and ask question.
Okay, so if there is questions, do not hesitate to interrupt me. So now I would like to give a few definitions before giving theoretical results. So first, let me define the additive and the multiplicative noise. The additive noise is as simple as the evaluation of our random fields at the optimal point. So basically, it's the noise when you evaluated the stochastic gradient at the optimal point. And the multiplicative noise is the difference between our random fields and the additive noise. I'm going to do a few assumptions on the multiplicative noise. I don't want to go too much in details. You don't need to read all of this, but I want to just highlight 2 points. The first assumption is very classical. This is an assumption that is made everywhere. But the second one is new. It's a proposition of our paper, and it's a holotype assumption because it depends on both the norm and the squared norm, instead of depending only on the square norm plus the term of constants here in the first line. So this is a new assumption. And what we show that, well, M1, so the first part that depends on the simplion's norm, well, if the random field is linear, like for sparsification, for instance, well, this constant is equal to 0. But for quantization, M1 is different to 0. Why is it the case? Because in expectation, the compression of the distance between the compression of 2 points Z and Z prime is bounded by 2 terms, one which depends on the norm and one on the squared norm. So this is why this assumption is relevant, and it is the key. It is a key to provide non-asymptotical results for compression. One last definition is the covariance of the additive noise, the covariance of the noise induced by the additive noise. We have in this setting an asymptotical result, which is an adaptation coming from Pollack and UDC 19.2, so it's quite an old result, which states that if we consider a decreasing step size, well, we have essential limit theorems that characterize the convergence of the Pollack-Rupert iterates towards normal distributions, which covariance is determined by the product HF minus 1, HF is the Hessian of our problem, the covariance of the additive noise, C ANIA, and HF minus 1. So ANIA stands for additive noise induced by the algorithm. So this is why we call it C ANIA. So this is a classical result, but now we want to have something that is non-asymptotic. So here is the result. So now we take it for a constant step size gamma. Under some assumption, we have that the excess loss evaluated at the Polyak-Rupert iterates is bounded by 3 terms. One, which is a bias term, which is a classical bias term that is the same from Bach and Moulin and Defosses and Bach. The second one is a classical asymptotic noise term that we have in the central limit theorem. It's a trace of C ANIA HF minus 1. And the last term is a term that comes from the multiplicative noise. So here it depends on the mu, the lowest eigenvalues of the Hessian of our problem, which is a problem because in Bach and Moulin, which basically analyze this square regression with averaging in one class, they do not have this dependence on mu. But here we have it, but it's asymptotically negligible if we take a step size that is decreasing or that is horizon dependent. So here, asymptotically, the dominant term is the square root of trace of C ANIA HF minus 1. And here, as I was saying to you, contrary to Bach and Moulin, the convergence rate is not necessarily independent of mu. And in fact, we also have a hidden dependence of mu in this term, in the trace of C ANIA HF minus 1. Why? Because imagine that C ANIA has terms that depend on the identity. Then the product C ANIA and HF minus 1 will make appear trace of the inverse of HF minus 1, which depends on mu. And this is why, even if we take step size here that is horizon dependent, which will make this quantity negligible, we might still depend on the constants of non-strong convex we might depend on mu. So this is why we need to examine the explicit formula of this quantity in order to determine the convergence rates and to know if it will depend or not on mu. Just I want, before computing these formulas, I would like to give the results in the linear case. So in the linear case, we assume that the multiplicative noise is simply equal to a matrix vector product with a matrix X, a big Z, which is not necessarily symmetric because of compression. And we assume that the square norm of the multiplicative noise is bounded by a term that now only depends on the square norm. So here M1 is equal to 0. And what we have something that is very close, but a bit different. So the two first terms are identical. This is the bias term and the noise that is asymptotically dominant. But here we have now a term that comes from the multiplicative noise, which is now independent of mu. So here it means, first it means that it's generalized Bach and Moulin, because here we have something that is linear, as in this work, and this result is the same as they obtain. And now we know that we will obtain a rate of convergence in 1 on k, if and only if the covariance matrix C ANIA can be bounded by terms proportional to the Hessian of the problem. So now let's compute this formula in order to know if we will suffer or not of non-strong convexity. So let's explain how to do it. So first of all, by definition, our additive noise is simply equal to the evaluation of our random field at the optimal point, which is the distance between the true model and the compression of the gradients evaluated both at the optimal point. This can be rewritten explicitly because we are in the least square regression framework, and this is equal to the compression of xk xk, x being the features, and epsilon k being the noise. And this is almost surely equal to the product between epsilon k, the noise, and the compression of our features. So this is not necessarily true in general, but this is true for all operators under consideration. So consequently, it means that Cn is simply equal to the product between sigma square, the variance of the noise, and the covariance of the compression of the features. So we now introduce an operator which we call the compressor covariance, which takes two parameters: one, the compressors, and secondly, a distribution. And then it returns the covariance of the compression of this distribution. And just note here that it's not enough to take as parameters the covariance of the distribution. We might have two different distributions with the same covariance that have a different compressors covariance. So this is why we need to take into consideration a distribution and not simply its covariance. And it means that to compute Cn, we simply need to compute these operators of covariance for each compressor. Let's do it. So on the plot on the left part, I will explain it in a minute. But now I just would like to focus on the right part, where I present a few formulas for a few compressors. So here is the first line in classical setting without compression. Well, the covariance is simply equal to the covariance of the original datasets, which is also equal to the Hessian of the problem. For partial participation, I have something that depends that depends also on the data covariance multiplied by a constant term. And so for sparsification, I have something interesting. I have something that depends now on the diagonal of H. For run H, it depends only on the diagonal, and for sketching, it's even worse. It depends on the identity. So here what we have two terms. One, which is a structured noise that depends on the original data covariance. And we have an isotropic noise, which makes the covariance inflate in every direction. And this is bad. This is very bad because this isotropic term significantly impacts the limit distribution with a rate proportional to the inverse of the Hessian. And this is why we might have compressors that have the same variance, for instance, partial participation and sparsification, but which have very different behaviors. So let's observe it in practice. So here on this plot, I have two settings: one with diagonal covariance and one with a non-diagonal covariance. On the x-axis, I represent the dimension, so I make vary the dimension, and on the y-axis, I represent the trace of Cn h-1. So here I represent in plain line the empirical trace, and in dashed line I represent the one given by the theoretical formula. So what I observe that sketching is skyrocketing, while partial participation, sparsification are here exactly identical, very close to run H. And suddenly, in the non-diagonal case, because of this isotropic noise, isotropic term, well, everyone suffer from non-strong convexity, and the trace is skyrocketing, while partial participation is not impacted. Okay, so I don't know if there is any question at this point. Okay, so I continue. So just to illustrate this phenomena of isotropic term in two dimensions. So here I represent two settings: one with covariance that is diagonal, one where it's on the upper where it's not diagonal, and on the bottom where it is diagonal. In blue, I have my original data sets with its covariance and its eigenvectors. And in orange, I have the compressed data set with its covariance. So if I took an easy case with round one, so here round one takes only one coordinate, which means that every compressed point will be on the axis. So very logically, the covariance of the compressed point will also be aligned with the axis and not with the original covariance. This is the first point. And secondly, we clearly observe here an isotropic term on every direction. And on the contrary, if the covariance is diagonal, well, there is no isotropic term, but there is the covariance is simply multiplied by a constant factor, and it's still aligned with the initial one. If we compare to partial participation, on the contrary, partial participation is always aligned with the initial covariance, and we always have this multiplication by a constant factor. If we compare now with sketching, so for sketching, we see that there is the covariance are still aligned, but the isotropic term appears, the isotropic inflation appears in both diagonal and non-diagonal case. And for the last comparison here with quantization, I have something that is interesting because I'm not multiplied by a constant factor. I simply have an inflation in the other direction, which means that here the area of the ellipse is smaller than in the case with partial participation. So here we see that we will have different conclusion for these different compressors. So now I would like to compare mathematically all these compressors. So we did it somehow with the previous plots in 2 dimensions, but this is not rigorous. So now let us put some math with it. So I compare here partial participation, quantization, and sparsification. They all have the same level of compression, so they all have the same variance. And I say that in the case of a symmetric matrix, partial participation and sparsification will be exactly equivalent. So this is what we observe. So it corresponds to this plot, and indeed partial participation and sparsification are exactly identical. And here I say that the trace will be of quantization will be larger than for sparsification and partial participation. And in fact, it might be by several order of magnitude larger. Now let me present another setting where we have a constant diagonal. So the diagonal of M is constant. This is the case after standardization, which is often done in machine learning. And here we have something that is different. In this setting, we can say that the covariance of quantization is strictly smaller than the covariance of sparsification. So here note that this is a result on the covariance directly and not on the trace, which means that here the ellipse. So here we are saying that in the case with a constant diagonal, this yellow, this orange ellipse is inside this orange ellipse, which we almost see it here, even if the diagonal is not supposed to be constant here. So and also when we compare to partial participation, it's still bigger, but now it's not of several order of magnitude, so it's comparable. So which is somehow what we seen at the plot where I was comparing the convergence of different compressors. I've shown one plot where partial participation and quantizations are almost identical. Now I would like to illustrate this behavior on real data sets. So let's do it step by step. So let me first explain what I represent. So here I have 2 data sets. Here it's quantum, a Tableau data set. On the x-axis, I represent the value of omega, so I make vary the level of compression. So here it's a low compression, here it's a high compression. On the y-axis, I represent the trace of Cyania H-1, which characterize the convergence of our algorithm. Here on the top, I represent the data after standardization pre-processing. here, when I compute a PCA, which makes my covariance being diagonal. And here on the bottom, it's the raw data without any preprocessing. So here, what I observe that so I observe this ordering, this relation of orders that I presented at the last slides. So here I have two regimes for quantization. So first quantization is very close to partial participation Brown, and then at some point when omega increase, it separates from partial participation, and it starts to be a bit to be worse. So and here the benchmark without compression is better than partial participation, which is itself better than quantization, which is itself better than sketching, round H, and sparsification. So this is exactly what was saying in the previous property. Next case, with a PCA, we now observe that every compressor behave well equivalently, except for sketching, which always have this isotropic term, and which suffer from non-strong convexity. And for raw data, I have no systematic order between compression schema, so there is nothing that I can say. Now for Sapphire 10, I made the same experiments, and I have that again. I have these two regions for quantization. Then for PCA, I observe that everyone is equivalent except for squishing. And for the raw data, it's very close to the standardized case. But here again, we cannot give any insights. I don't know if this is clear. If you have any question, please feel free to interrupt me. Just to give you a few insights on the data itself, just to explain why this is the case. So here I represent the covariance of Sapphire 10 and Quantum in two cases, for raw data and standardized data, for quantization here and sparsification. So here for raw data, I observe first only full points when it's not standardized, because these full points have a very high magnitude. And if I standardize it, I observe a different structure, which with a very strong diagonal and a kind of square here. And for Sapphire 10, I observe here a diagonal structure. What I observe that if we compare quantization and sparsification, for a low omega, quantization much better preserve the data structure, the data covariance structure. And this is consistent with all the previous figure, because the traces for quantization were indeed smaller than for sparsification. So this is what we observe here. Here for small omega, so here it's omega equal to 1. The trace is much smaller than for sparsification, which is here. And when we increase omega, well, it's closer to sparsification. And this is what we observe here. Here, the structure between a small omega and a large omega is very different. Low omega have a much better preservation of the structure. And this is true for both Quantum and Sapphire 10. And so this will be also consistent with the gradient descent that I will show you later, where quantization outperforms sparsification. So at this point of the presentation, I would like to give a few takeaways before applying this to federated learning. So first, I would like to say that quantization is not Lipschitz in square expectation. So it could not be analyzed by my previous analysis on linear stochastic approximation, but it satisfies a holder type assumption. And this is why we can analyze it. And we can show that while its convergence is degraded, it yet achieves a rate of convergence comparable to projection-based compressors. The second very big takeaway is that if we have two compressors that have the same variance, so let's take for instance round 1 and partial participation with probability 1 on D, they have the same variance, so they verify the same assumptions that I show you at the beginning of this presentation. but we show theoretically and empirically that partial participation is much more robust to ill condition problem, and that they do not have the same behavior. And the last takeaway is that if we have standardized features, then quantization is much better than sparsification and randomized coordinate selection. And if not, then quantization will be worse. So I want to come back to the comparison between my 5 compressors in 4 different scenarios. And I want to emphasize that we can perfectly explain why they have different behaviors. So here in the first setting, I have a fast eigenvalue decays. So I am in a non-strongly convex setting, but I have a diagonal covariance H. In this case, our theory says that every compressor will behave well. They will not suffer from non-strong convexity, except for sketching, which always has this isotropic term. Here in the second scenario, I still have a fast eigenvalue decays, but now I have a non-diagonal covariance H. Therefore, every compressor will suffer from non-strong convexity and will start to converge at some point because of this term that depends on mu. Except for partial participation that do not present this isotropic term here in brown. So here it has this linear convergence in a log-log scale. In the third scenario, we have a slow eigenvalue decay, which means that we are in a strongly convex setting. And even in the case of a non-diagonal covariance, we do not suffer from mu, and we have this linear convergence in a log-log scale. And last case, it's alpha 10 with standardization. So the diagonal of the covariance is constant. And here, as I presented in the property comparing quantization and sparsification and partial participation, well, quantization in yellow is as good as partial participation, which is itself as good as the benchmark without compression. So we can recover the benchmark without compression, while sparsification, sketching, and partial participation all behave very badly and start to saturate at some points. So now I would like to apply all these results to federated learning. So I will speed up a little bit. So now we
have one quick question. Like, if
sure.
you go back to your slide, I think was 16. Oh, yeah, like 2 more slides. Yeah, this one. Sure. So with this, if you know what's the structure of H, can you actually design, like, given, let's say, constraint on W, can you say, like, what is, given your assumptions, given the structure of H and structure of noise, like, can you actually design what is the optimal compressor given all of these?
Okay, so about the optimal compressors, so I do not have a result that say, well, this is optimal in this situation. I only have a comparison between compressors, because here I compute the trace of, so I compute the covariance matrix only for 5 compressors that I can compare. So I can say that if H has this property, then this compressor will be better than this one, which will be better than this one. So I don't have notion of optimality, because I'm only comparing 5 compressors, and I present relation of ordering between these compressors. So it's the point of this proposition. So here, this is a summarized proposition. I have something that's go more in details in the 4 papers. But here, basically, I can give a comparison for a different setting, if H is diagonal or not, if the constants of the diagonal is constant or not, if it's strongly convex or not. So based on these different properties of H, yes, I can say which compressors, based on the 5 ones that I present, I can say which one will be the best. So it's yes to a question, but here I don't have the notion of optimality. So I don't know if it's answer to your question.
I think, yeah, it answers. Thank you very much.
Thank you. So now let's apply to federated learning. So now we have n clients, which all compress their gradients, and we average this all together. So it means that the random field is simply equal to the difference between the true gradients and the average of the compressed gradients. And we will consider two scenarios. One, which is coverage shifts, where we have heterogeneous covariance. So each client have its own different covariance. And the other setting is the optimal point shift, where each client have its own optimal points, which is possibly different to the one of another client. Let me just state that the theorem 2 and 3, which gives the non-asymptotical results in the nonlinear and linear case, they still hold. So now everything what we have to do is to compute the matrix C ania. So the question is how to compute C ania. So here, just to, I will not go in the full details, but basically, now we have that C ania. So we follow the steps that I already presented you before, and we have that C ania is simply equal to the aggregation of all local compressors covariance. So here, if we have one client, we simply remove this sum, which means that that's just the aggregate of local covariance, which means that in this setting, most insights from the centralized case remain valid, and we can state that the coverage shift case in federated learning is exactly equivalent to the case with one client. Now the concept shift is a bit more tricky, and in fact it will hinder the limit convergence rate. So now why is this the case? Because now the stochastic gradient evaluated at the optimal point depends on the optimal model shift between the global optimal model W star and the local optimal point W star I. And consequently, the matrix C ania depends on two terms. One, which is again an aggregate of covariance of compressors covariance, but here observe that the distribution do not depend on H, but on big theta I. And this covariance big theta I is the distribution of our stochastic gradient evaluated at the optimal point. There is also another term that depends on the covariance of the model shift, but we can discard this and upper bound only by this quantity. But here, so here's being dependent of this quantity is a problem. It's a problem, and why? Because just to give you insights in a more simple case of linear compressors. For linear compressors, C ania is a linear function of this quantity, of the average of this covariance. And we can upbound this covariance by two terms. One, which is the classical case of the homogeneous setting or the coverage shift. So this is what we had previously. And the second one is the impacts of dispersion of the optimal points. And this is why this is a term that hinders the limit convergence rate. So which say that we cannot have exactly the same rate of convergence as before. So yeah, the convergence will depend on the shifts between the local models and the global models. And very obviously, if every local optimal models are equal, then this term is simply equal to 0. And we recover the homogeneous case. Just to give a few experiments before concluding this presentation. So here I have two cases, coverage shift and concept shift, with synthetic dataset here and here, and on the center real datasets. So here I have no shift, so it's a federated setting with all homogeneous case, so they have the same data distribution. And what I observe exactly what I observed in the central in the case with one plant. So here nothing changed. In the case with heterogeneous setting, so with different covariance at each client, then what we have that the covariance the covariance of the compressors is a difference. It's the average of all compressors, but it's more or less equivalent to the case with one client. So it's not a problem. And here with real data sets, what I observe, so this is with standardization again, I observe that quantization behave exactly like partial participations, which makes it very competitive compared to sparsification and sketching, even if S quantization is supposed to suffer from isotropic time. And for concept shift, so it's a bit harder here. I represent a few more things. So here I represent the how to say that the convergence for two kinds of algorithm. One without control variates, so it's in plain lines, and one with a control variate, so it's a term of memory, exactly like in Dyna and Artemis, which has been published 5 years ago. And on the top here, it's with a batch stochastic gradient, and here with a true gradient descent. And here, what is very interesting, there is 2 points that I want to highlight. The first one is that for here in blue, that is a little bit hidden by the dashed brown line, we observe not a one-on-key rate of convergence, but an accelerate rate, which depends on one on key power 2. And this is an acceleration, and this is what this comes from the biostem that I presented you at the beginning of this presentation. The biostem had 2 terms. One which depends on one on key and one on key 2. So here we observe it. And also what we observe is that partial participation with a term of memory in brown recover exactly the benchmark. So we do a compression, but it's exactly like the benchmark. This is a behavior that is expected. In a previous paper in Artemis, I proved that that memory will reduce the impact of heterogeneity and might even cancel it in some setting, and in particular in the setting where we use a true gradient. So this recover existing results. And here in this paper, we have a social limit theorem on this algorithm. So to conclude this presentation, I want to summarize the contributions of my article. So first, I analyzed in all generality the setting of the problems, the linear stochastic approximation problems. I analyze them under weak regularity assumption on the random field. So we do it by providing a holotype assumption, which is a new assumption that has never been considered in any previous work. We provide non-asymptotic theorems. We underline the key impacts on convergence of the Agna's covariance C-Agna. We describe the link, the relationship between the compressor C, the features covariance H, the echelon of the problem, and the Agna's covariance C-Agna. And we explain exactly what makes this converge or not. And we also explain how to compute the Agna's covariance C-Agna, and we applied to the federated learning setting with heterogeneous clients. So the big takeaway of this presentation is that we go beyond the worst case analysis of compression. We analyze and compute the compressor's covariance, and we show that there is difference between compressors that have the same variance. So, but that was never underlined before. So two compressors, same variance, but different covariance and completely different behaviors in different settings. So this summarizes the contribution of this paper, and I will stop here. So thank you very much for your attention, and if you have any question, do not hesitate. Thank you very much.
Thank you, Constantin. It was a very nice talk. Are there any questions? So if any, please just feel free to unmute yourself and ask a question. Okay, so let me just start. What I wanted to ask is, uh, so you analyze just like that each of in federated learning setting that each of the client just computes the gradient and compress it and sends it back to
Yes.
the server, right? Like one alternative how to also get a better communication or communicate less is to run local updates before communicating back your updates. Do you think that you could extend your framework to also understand the impact of running the local steps as because of because of the mismatch of data is also like another way how to like analyze whether I should like also compare whether I should take local stems or whether I should use the compression or
Okay,
combine both,
so
right?
yeah, so this is a very good question, and in fact, I wrote it as an open directions. So
Okay.
this is the first open direction here. We could completely consider as a scenario where each client run several local iterations before sending their update to the central server. This will indeed reduce much further the cost of communication. But here, the challenge is that the additive noise will be more complicated to compute. It will be different because here the additive noise was simply the difference between no, so the additive noise was the evaluation of the noise at the optimal point. And here we have something that is different, and the additive noise covariance, CNR, will also be different. So this is a challenge. I think this could be done, but it's not completely straightforward, as it requires more work on the additive noise to focus on the spots and to find a new formula um, for the matrix C area. And maybe we might have something that is a bit different. I haven't run experiments in this setting, but this is very interesting to consider also. So yes.
Yeah, thank you. And when I see this slide, could you please comment on what do you mean on of incorporating high order bounds as a is it
Okay.
direction?
So yes, here this is a very large open direction. But here my point is that so if I go to the very beginning, well, I will not go to it, but the classical assumption is on the expectation and on the variance. And here we also consider the second the covariance to provide a much tighter analyze. So here one natural question will say to, instead of just considering the expectations, the variance, and the covariance, to go to a higher bounds of our moments and to see if there is not something more tight that can be said. So this is the idea.
Thank you. Are there any other questions? If not, thank you a lot, Constantin, for your talk. We'll soon
Thank you very much.